So what does it mean to solve? So welcome to day 4. We're going to solve equations. We're going to use logarithms to solve situations, and we'll talk about why and how we use them. So solving means to find the truth. When I solve something, I'm finding the true result. So when we solve something, we are finding the values of the variables that makes the problem true. There could be more than one solution, but we're finding the truth. So how do we solve something in math class? What do we need to do to solve? We need to isolate the variable, and we're going to, by using inverse operations. So we've been doing this for a long time. You know, to solve a problem with addition, we got to use subtraction. Something with division, we got to use multiplication, and so on and so forth. So today we're going to talk about using inverse operations. So on homework 40, we had this problem, and what we needed to do to solve this problem, we needed to get this part of the problem. We had to isolate this whole log and set it equal to a number, and then we did something called the curl. And that's what we did. We isolate the logarithm and then we curled it. So if you remember what we did to get this by itself, we subtracted 4. We divided by 3. And we have log base 8 of x minus 3 is equal to, and when I curl it, I start at the base 8, I get 8 to the 1/3. Oop, I'm sorry. Just 1/3. I have log base 8 of x minus 3 is equal to 1/3, and I curl it. I get 8 to the 1/3, which is equal to x minus 3, and 8 to the 1/3 is the cube root of 8. So I basically have 2 equals x minus 3, and I add 3 to both sides, and I get x is equal to 5, and that is my solution. That is what would make this problem true. And this is what we did on homework number 40, isolating the problem. So for a log problem, the previous problem, we had to isolate the log, and we had to curl it, and curling it is kind of making it into an exponential. So when I have an exponential problem, that means the variables in this exponent, again, I need to isolate, except this time I need to isolate the exponential part, which is going to be raised to the something is equal to a number, and then I'm going to log both sides of the problem. So here's an example. I have an exponential 2 raised to the x is equal to 1,000. I'm going to have to log it at some point. So I rewrote the problem, and the first thing I'm going to do, I'm going to log both sides. I'm just going to use my general common log, that basic log key that I have. I'm going to do both sides of the problems, and the log goes in front of the numbers. But if I remember using my properties of logarithms, this x jumps in front. So I can rewrite this as x times the log of 2 is equal to the log of 1,000. Now I'm solving for the letter x. That's what I'm always solving for. So log of 2 is just some number. We talked about this the other day. It's just some decimal number. So basically, x times a number is equal to another number. So all I have to do is divide by that number. I have x is equal to log of 1,000 over log of 2. I'm going to put this in the calculator in a minute, and I'm going to get a result. But here's what we're going to learn. This fraction is the exact solution, and when I put it in the calculator, I'm going to get a rounded solution. Okay, sometimes I want the exact, sometimes I'm okay with rounded, and I'll tell you exactly when I want either one. So I'm going to type this in my calculator, log of 1,000, close my parentheses, divided by log of 2. Let the calculator do the whole hard work. And I get this number here. I'm going to put this on my, here, I'm going to write it as, rounded as 9.966. And that is my rounded solution to this problem. I could put this back into the original problem and I should get the same. In fact, let me try it. I'm going to cheat here a little bit. I'm going to do 2 raised to my answer here. And if I did this right, I should get 1,000, and I do. So it does work out. Now there is another way to do this, because we do have that special key if you have a newer calculator. So I have my original problem, 2 raised to x is equal to 1,000. And to get rid of an exponential base 2, I have to use a logarithm base 2. What do I do to one side? I do to the other. And the idea is that log base 2 and 2 exponential base 2 cancel out. I have x is equal to log base 2 of 1,000. I could put this into the calculator, and let's see what I get. So I go ahead and type it in my calculator using that special math key and going to letter A here. Log base 2 of 1,000, and you can see I get exactly the same result as I had before, and I should, because of that whole change base idea that we talked about last time. And so I get 9.966. Again, log base 2 of 1,000 is my exact solution, and this 9.966 is my rounded. Okay, and sometimes I do want rounded. Okay, this next problem, I do need to isolate this exponential part, so I'm going to add 3. I'm going to divide by 2, and right now I have 1.2 raised to the x is equal to 9. And if I wanted to, I could do that whole special way of doing it, and I'll come back to do that. But what I normally do, I just log both sides. So when I log both sides, this x that's in the exponent drops in front. I have x times log of 1.2 is equal to log of 9. And then I could just divide by this log of 1.2. I get x is equal to log of 9 over log of 1.2. That is my exact solution. I'll type that in the calculator in a minute. Or the other way is when I had 1.2 to the x is equal to 9, I could have done that whole log base 1.2. I could use really any base I want for logs. These cancel. I get x is equal to log base 1.2 of 9. And you'll see that this solution will be exactly what that guy is, because of the change base. And I'll go to my calculator and I will show you that. Go to the calculator, log 9, close parentheses, oops, didn't close my parentheses, divided by, don't forget to close your parentheses, that does make a difference. I get 12.051, or if I use that special math key, going up to A, log 1.2 is my base, my number is 9. You see I get exactly the same solution. They're both the same. So you can see how I got my solution. Like I said, you could use that special key to get the solution, or you could use, I just rather use logarithms, so I don't have to go searching for that special key. But you can see the pattern that I'm getting here every single time. So again, when I solve these problems, I'm not going to use that special log key too often. I mean, you can, but I just rather just log both sides. And know that this x drops in front. I get x times log of 1.06 is equal to log of 4.1. And to get x by itself, I just have to divide by log of 1.06, log of 1.06. I get x equals log of 4.1 over log of 1.06. And you could trust me, I put this in the calculator, and I got 24.215. Or you could have just done log base 1.06 of 4.1, and you would have got that same result. The next problem, I need to isolate, so I have to get rid of the 2. I have 5x to the x over 4 is equal to 75. I'm going to log both sides. And when I log both sides, this drops in front. So I have x over 4 times log of 5 is equal to log of 75. and I decide I need to get rid of this 4 on the bottom, so I multiply by 4, and when I do to one side, I do the other. These 4's cancel out. I have to divide by log of 5. I divide by log of 5, and these cancel. And now I have x is equal to 4 times log of 75 over log of 5. And I put that in the calculator, and I get 10.730. And if you want, you always could check by taking your result and putting in the original problem to see if you get the answer that you want, the result that you want. Now this one is similar to the ones we've done before. It is an exponential. My variable x is in my exponent, so I'm going to use logarithms. But since I see an e to the x, I'm going to use my ln of x key because they are inverses, so they undo each other. So I am going to get rid of this 50 because I want to isolate that exponential, so I have e to the 0.035x is equal to 4. And now, instead of log, I'm going to use this ln because a natural log has a base e, so these cancel out. I have 0.035x is equal to the natural log of 4. Again, it's very easy to get rid of this just by dividing by 0.035, 0.035. I get x equals the natural log of 4 over 0.035. And I'm going to put this in the calculator. I'm going to show you I'm going to put this in the calculator because I'm not using that log key. I'm using this ln key. So I have to do ln, which is underneath the log key of 4, close your parentheses, and divide by 0.035, and you get your results. If you saw it, I did it kind of quick, and I get 39.608. 39.608 is my final result. Nope, that's not good. 608. So all the problems that we're going to do today, we solved before break using our graphing calculator and finding intersections. This time we're going to use logarithms. So my first one I'm going to use is country A is growing. So I have to do 1 point plus 0.02. So A is equal to 5, 1.02 raised to the x. Then I have country B, which is also growing. So I have to do 1 plus 0.05. I get B is equal to 2, 1.05 raised to the x. And instead of doing this in the graphing calculator, I'm going to make these equal to each other. 5, 1.02 to the x is equal to 2, 1.05 raised to the x. And then I say to myself, I need to isolate b to the x is equal to a number because that's what I've been doing. I'm always isolating that exponential part. So I want to get the exponentials together, and I want to get those initial values together. So I'm going to divide by 5, and these cancel out. And then I'm going to divide by 1.05 to the x and 1.05 to the x. And these two cancel out. And when I rewrite this, I have 1.02 over 1.05, both raised to the x, is equal to 2 over 5. You can just leave it as a fraction. And now I can log both sides. And this x jumps in front. I have x times log of this ugly fraction is equal to log of this fraction. Not as ugly, but still a fraction. And then I could just divide by log of this ugly fraction. And I get x equals log of 2/5 over log of 1.02 over 1.05. And I put this in my calculator, and I get 31.610 years is how long it would take for those two countries to equal each other. And I would get the same result if I put this in the graphing calculator and see where they intersected. I think what you can see, though, is that this x value is equal to log of one population over the other divided by log of one of the rates over the other rates. Notice the fractions are upside down from each other. But that's kind of what I have here. If you look at these fractions, this was A2, this was A1, this was B1, this was B2. Now we have to figure out half-life. So I want to figure out the half-life of tritium, which decays by this rate. So if it's decaying, I have to do 1 minus 0.054. So for my half-life equation, or for my equation for this, I get 0.946 raised to the x. Notice I didn't put an a value up front. I'm not going to, because the a value is just going to be 1. Because the other equation I want to use is the half-life, and the half-life is just half of that amount, which is because that would be the half. Now, normally we put these in the graphing calculator, we see where they intersected. Now I'm going to see where I'm going to set them equal to each other. 0.946 raised to the x is equal to, I'll make it 0.5, make my life easier instead of a fraction. I'm going to log both sides. I'm going to log both sides, and this x jumps up front. I get x times log of 0.946 is equal to log of 0.5, and I divide by this. I get x equals log of 0.5 over log of 0.946, and I put this in my calculator. I get the half-life is about 12.5 years. Now if I pay really close attention, my half-life is going to be x is equal to log of a half over log of 1 minus whatever my rate was. My rate for this one was this. And that will be my half-life. And this is how I could do this without using the graphing part of the calculator. I could use logarithms instead. It's better to use logarithms. It is more exact. Okay, doubling my money. Let's see what I can do to double. So I have this problem right here. I could write it as y1 equals 1200, 1.0325 to the x. Because when I do 1 plus 0.0325, because it's growing. And my second one I can make double, which is 2400. And the question is, do I really need the initial value? Well, what I would do, I would set them equal to each other. And the first thing I'm going to do is divide out by the 1200. I get 1.0325. I gotta find my eraser. Raised to the x is equal to 2. So do I need the initial amount? No. Double is double, because what I'm really getting is this equation. The x moves up front. X times log of 1.0325 is equal to log of 2, because it's double. I divide by this, log of 1.0325. I have x equals log of 2 over log of 1.0325. And I put this in the calculator, and I get 21.672 years. And remember, if this was my form for my half-life, I think the form for my doubling is x equals log of 2, and now it's over log of not 1 minus r, 1 plus the r, because it is growing. And here's my r value right here. And there we go. That's how I figure how long it takes to double. And the initial amount is irrelevant. Just like for the half-life problem, the initial amount is irrelevant. That's why I made it 1. So is it possible to take a log of a negative number? Well, let's see. Let's do log of negative 10 equals some number x. Well, if I recall, the base is 10 here. If I curl this, I get 10 to the x is equal to negative 10. And I know that this is impossible. I can never raise 10 to some exponent and get a negative number. So is it possible? The answer is no. So you can never take logs of negative numbers. So we're going to use this idea when we solve today because, again, if you remember from earlier in the year, I may do everything right algebraically, but I could get false solutions, and they're called extraneous. So for this example, let's see what we got here. We're going to use our properties. Well, I see a minus sign here. That means I could do log of 1 plus x over x, because I could divide the quantities when I subtract logs is equal to 2. I didn't see a number here. Oh yeah, it's 10. And now I could curl this. I get 10 to the second is equal to 1 plus x over x, and 10 to the second is equal to 100. And I don't like having x on the bottom, so I'm going to multiply this side by x, that side by x. I get 100x is equal to 1 plus x. I subtract one of these x's, and I have 99x is equal to 1. I solve for x, I get x equals 1 over 99. If I wanted to, I could plug the solution in for these x's, and I could show that you would get 2 as a solution. And 1 over 99 is fine, as long as it's positive. So for this next problem, because I see addition, that means I can multiply the quantities. Don't forget there's a base 4 here, so it's log base 4, x plus 1, x minus 5 is equal to 2. And now when you curl it, you get 4 squared is equal to x plus 1, x minus 5. Well, 4 squared is just 16 is equal to, and I'm going to expand this out using my Algebra 1 skills, and I know when I do this, I have to make it equal to 0. So I have 0 equals x squared minus 4x minus 21. I could factor this one easily, and I get 0 equals x minus 7, x plus 3. That multiplies the negative 21, adds the negative 4 in the middle. I get 2 solutions. My 2 solutions are going to be x equals 7 is a solution. My other solution is x equals negative 3. Except, I can't use that. This is extraneous. Because if I plug negative 3 in here, I get negative 2 and negative 8, and I can't take logs of negative numbers. Okay, so when we do this problem, and I did everything right algebraically, it's just that I cannot log a negative number, so 7 was fine. I can plug 7 in the original problem, it works. I can't use negative 3. So this one I see a couple of things going on. I see a plus sign here, and I see a coefficient that I can move over here. So I have ln of x minus 3, x plus 4, because I can multiply when I see addition, is equal to ln of 2 to the third. And now I see I have single logarithm on each side. So this one ln, it doesn't matter what log it is, as long as they're the same base. It could have been log, it could have been ln, it could be log base 3. They cancel, and now I have, I'm going to multiply this out, x squared plus 1x minus 12 is equal to the third is 8. I subtract the 8. I get x squared plus x minus 20 is equal to 0. And now when I factor this, it's pretty easy to factor. This is x minus 4, x plus 5 is equal to 0. And when I solve this, I get a couple solutions. I get x equals 4, which is a good solution. And I get x equals negative 5, which I know is extraneous, because I cannot get a negative as a solution for x because I can't do logs of negative numbers. So I can't do that. Now this last one, this is as tricky as whatsoever. It's like, holy crap, I have e to the 2x, I have e to the x. It's a lot going on here. So I'm going to use a substitution trick. And the idea is that I'm going to let w, you could choose any of your log you want. I'm using w. I'm going to let w be e to the x. I'm going to let w squared be e to the 2x. So I could rewrite this problem as 3w squared plus 5w. I'm going to subtract the 2 over to make my life easier. Now I can factor this. So you've seen I've made my little x, and I factor it, and I reduced it, and now I'm going to be able to solve this. I have w is equal to 1/3. I have this one as w equals -2, but I'm not really solving for w. I'm solving for x. So I got to go back and remember that w was e to the x is equal to 1/3, and e to the x is equal to -2. So how do I get rid of that e with e to the x? Oh yeah, my logarithms. ln, 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 and these cancel and these cancel. I have my solution is going to be, let me see if I move it up, x is equal to the ln of 1/3. I put that in my calculator, I get -1.099, and then I have x equals ln of -2, which I know is impossible. I cannot do logs of negative numbers. So there's my one solution.